So can we talk about noise? There are many types of noise. When we say QRN or QR Nancy, we're talking about mostly noise either from natural causes like static and lightning and storms, that kind of thing, or we're talking about man-made noise. Man-made noise is getting kind of annoying lately because we're getting into the summer months. And what happens during the summer months? We start to turn on things like our pool heaters, our solar systems are online with these inverters that make a lot of noise, and there's a lot of problems with power lines that show up once they get wet in the rainy season. So here in the northern hemisphere, we're well into the spring season, coming on to summer, and there's all kinds of crazy local noise sources that we're encountering. Now, if you like to hang out on 80 meters or 160 meters and even 40 meters, these local noises can really ruin your day and make your ham radio activity kind of very painful. So in this video, we're going to study what we can do about these local noises, usually man-made in nature, and how we might mitigate them by using some electronic means. So I built this noise canceling system, which is all tube type. You know, I like to design with tubes, but some of you out there would rather build a noise canceller that's solid state. So I thought we'd start with a solid state noise canceling project. And we're not going to invent something from scratch. We'll take a tried and true kind of circuit topology that you might find out there in some of the commercial units, and we'll modify that a little bit and simplify it a little bit and stick it in this nice case that I picked up, and we'll see what we can do with noise cancellation in this video. Of course, we all know the bottom of the broadcast band, especially from 550 kilohertz up to around a megahertz. You can get a lot of noise. And I'm down here at below the broadcast band, so I don't have any interference. You can just hear the noise. It's pretty significant. And this is where a noise canceling system can help you out a lot on broadcast band monitoring. Of course, noise can come in almost any frequency, but it seems like a fairly periodic noise related to something like a generator or motor. It's a pretty low frequency. So as we tune, see, we're hearing periodic harmonics of some noise source, probably down in the 100 kilohertz region, since it seems like every 100 or 50 kilohertz we get the noise. By the time you get up to 80 meters, you know, that noise might be right in the middle of the frequency you're interested in. The noise can pick up again as you get higher in frequency. Quite a bit up here on 10 meters. So I don't care if you've got a very expensive receiver. When you have man-made noise like this that you're dealing with, you lose the edge. You lose all that sensitivity that's built into the receiver. Not to say that even simple receivers are not affected by noise. The star roamer is very upset as well. But what's even worse, the Watkins-Johnson itself is offending the little star roamer. In fact, the little star roamer is probably offended that it should be desensed with noise coming out of the Watkins-Johnson digital electronics.
We should probably talk about noise a little bit. I saw this interesting slide on the internet, and he calls man-made noise of any kind, including ham radio signals and spurious signals and harmonics of signals, in other words, intentional radio transmissions, QRM. But he also lumps in all the other man-made noise as well. Noise from solar panel inverters and lights and different types of switching power supplies and receivers and set-top boxes and TVs. And he puts QRN in a completely different category. He reserves that for natural noise interference. I don't know, it sounds kind of wrong to me, but I'm going to defer to this definitions. Any comments, put down in the comments section. Let's see what you guys think about the definition of QRM and QRN. So I'm just going to show a picture of a typical noisemaker that people are running into more and more nowadays. And that is these solar setups that you're seeing on your neighbors' houses. Maybe you have one yourself. It's basically a DC AC inverter, and this guy can be any one of about 5 different technologies. Maybe they thought about EMI and emissions coming out of it, both conducted and radiated, or maybe they did not, but they definitely got their product on the market, and we are seeing some noise coming out of these units. Of course, the classic street lamp with the bad bulb, and the different types of pool heaters and set-top boxes and cable systems and modern television and so on. These all are big noisemakers that we have to contend with today. Before we get too deep into noise, let's talk about the noise that's generated inside your receiver. That's right, your receiver itself is a noisemaker.
So let's talk a little bit about receiver noise and sensitivity. I always try to warn you guys about the boring parts so you can skip them. But there's a useful receiver sensitivity chart at the end, at least, before we get into noise cancellation. So first of all, what is your receiver's sensitivity? We normally measure this in microvolts, into 50 ohms and a certain bandwidth. dBm reference to 1 milliwatt is another way to describe it. So we talk about minus 120 dBm as being sensitivity of a receiver. Noise power is the magnitude of the noise described as NP equals KB T0B, where KB is Boltzmann's constant, 1.38 times 10 to the minus 23 joules per degree Kelvin. And the next T0, that's room temperature, or 290 degrees Kelvin. And then finally, B is the bandwidth of your receiver. What is the setting of your receiver's bandwidth, or your overall bandwidth of the channel? So for a receiver with a 1 hertz bandwidth, the noise power would be 1.38 times E minus 23 times 290 degrees times 1 in watts, and this comes out to minus 174 dBm. It is often described as minus 174 dBm per hertz of power spectral density, PSD. So for a receiver with a 1000 hertz bandwidth and a 10 dB noise figure, the noise floor would be minus 174 dBm plus 30 dB, which is 10 log of 1000 hertz, plus 10 dB, that's noise figure, and that can be added directly, and you end up with minus 134 dBm. That's kind of your minimum discernible signal in the receiver. It doesn't mean you're going to hear anything that you can recognize. To actually hear the signal well, you might have to add a few dB. So I promised a chart at the end of this section, and This is a chart that I got off the internet. It's pretty useful. It talks about S units and receive voltage sensitivity. But I decided to do my own chart, which opens it up a little bit, gets it down to that minus 134 area, which I think is normal for a very good receiver, all the way up to the 1 milliwatt, where you're blasting the receiver with an input. Generally, sensitivity decreases in your receiver when the bandwidth increases, the temperature increases, your amplifier noise increases, or you start putting attenuation up front. So I don't care if you've got the best receiver in the world. I've got the Star Roamer here. Maybe this isn't the best receiver in the world, but I don't care what your receiver is, whether it's this little dongle SDR or the Star Roamer or the R390. There's another source that can cause your receiver not to be sensitive. And that source is noise that can cause desense. Or, even though you've got a very sensitive receiver, the noise that comes in is so much higher in amplitude than the signals that you're trying to receive that it makes the receiver look like it's acting like a little dongle or a Star Roamer. So this is the quickest way to make a bad receiver look good or a good receiver look bad, is the addition of noise. And I'm specifically going to show a chart here that's dealing mostly with lower frequency noise, because it's really HF is what we're talking about here. High frequency communications, atmospheric noise, man-made noise. What are these noise sources doing at these low frequencies? We've already proven we've got a pretty good receiver. We've got a good noise figure. We're able to pick up signals at a very, very low level. But look at how high those noise levels are. They're so much higher than the noise figure and the noise sensitivity of our receiver that they easily overwhelm the receiver's sensitivity. So let's talk a little bit about noise cancellation and trying to eliminate static and noise. Some noise can be reduced fairly easily at the end of the chain, sort of like post-processing, by using traditional clippers like diode clippers and audio filters, and of course lately audio DSP techniques. Periodic noise is fairly easy to handle with blanker type systems, which can be installed in just about any part of the receiver chain, from the front end to the IF through the audio chain, with varying effectiveness depending on how complex it is. Some companies went as far as to make a whole separate receiver front end or back end, and then they combine the noise receiver's output with the main receiver's output and try to eliminate the noise. For more randomized and non-periodic noise, especially with close-in noise, the front-end cancellation technique has been employed almost since the dawn of radio. This technique usually uses an identical antenna or an antenna that's specific to the polarization of the noise. In other words, a dedicated noise sampling sensor. The basic technique for noise cancellation is as follows. Consider a desired signal and a noise signal that's significant in amplitude and strong enough that when mixed with the signal you're interested in, it's going to cause trouble. If the same signal was introduced, and I'm saying the same noise signal was introduced, 180 degrees out of phase and at the proper amplitude to perfectly cancel the noise signal, the desired signal could be recovered without the noise signal. It's a tricky situation, but you can do it. You can null out the noise. There were many pioneers of noise reduction or static reduction technology. A couple of them were Roy Wigant, a Canadian-American. I believe he was born in Ontario, grew up in Vermont, worked in the American radio and the Canadian radio industry. And the other was Greenleaf Picard. Greenleaf Picard was an American, I believe, born in Vermont, and also worked in the radio industry in the USA. The techniques that these two guys came up with are easily 100 years old. Both of the applications that I'm showing you here are 1920 or before, and some, of course, were granted later. There's much talk about if the antennas should be identical and separated widely, as in a true diversity fashion, or if there should be a separate, smaller, local vertical antenna, and that vertical antenna is usually known as the noise antenna. Well, the answer really is yes, and that's shown in the patents. Both the identical antenna and the vertical antenna are shown in the patents, and this means that there are some cases where you need to use one and some cases where you need to use the other to effectively cancel the noise. So, little more than two antennas, a phase switch, some kind of phasing adjustment, amplitude adjustment, and finally a combining network are required to cancel static and noise sources. And almost any technique or device can be employed to do the math of the signal combining.
So we should probably talk a little bit about antennas when it comes to noise cancellation techniques. And many of these boxes have been out for years now. We're probably on the third generation of noise cancellation devices that the ham radio operator or the shortwave listener can purchase. There's been a lot of homebrew activity and lots of things in magazine articles and on the internet if you want to roll your own noise cancellation system. And they vary from passive systems to active systems, and it's a tried and true, a proven situation. Now, one thing you'll see on some of these boxes is a whip antenna. Now, this local whip antenna is going to be effective for stations where you have the noise source probably right in the shack, very close to where you're, to where you're operating. But for the most part, you're going to want to use the auxiliary antenna or the connection on the back that takes you to an external antenna that can be placed closer to the noise source. So for severe local noise cancellation, I'm talking about, the neighbor that has the solar inverter or the cable system or some type of generator or motor or arc welder that's coming up in your nearby factory. You need to have an antenna that can specifically pick up that noise signal. Most of the noise energy is fortunately in the vertical plane, so we like to use vertical antennas to pick up the close-in noise. I found when I had in one of those power poles with a light on the front of my house where the light was malfunctioning, that simply coupling right to the power line gave me a good way to drown out that AC hum. So I didn't even need an antenna. I simply used the power line as my the power line ground as my reference noise source. So if you're in a quiet location, okay, and now we're talking about DX, and you're trying to pick up signals that are coming in by skywave, long distance communications, it's been proven that using two identical antennas is the way to go, because the noise may be riding in from a long distance as well. So you would not use a simple vertical whip when you're talking about picking up a station in Florida that's coming out of New England. So using identical loop antennas, using identical dipoles, or identical ground-mounted verticals is the way to go if you want to get excellent noise cancellation in a fairly quiet location at your QTH. Now, if you have modest local noise, I still suggest that you use identical antennas. This really gives you the best chance of getting the noise cancellation. Also, using identical antennas allows you to take advantage of beamforming and actually improving by putting the desired signal in phase. So you're using your noise canceller kind of like a phase combiner between two signals. Now, you might have heard the term space diversity. Space diversity is where you have two antennas that are separated enough that when you have fading or multipath interference, that one antenna will still have the signal even if the other antenna has a dropout. Well, that's a great idea for fighting fading. It's not a great idea when you're doing noise canceling. You need to have the antennas closer together so they both are in the same fade and they're both basically in a similar phase situation. That's going to give you the most effective noise cancellation. So you really want those antennas to be closer than the old 5 to 10 wavelength rule for diversity antennas. Finally, there's some people that are using low noise receive only antennas. Active loop antennas, large passive loops, loop on the ground. These are all techniques that have become quite popular for hiding your antenna or small space type situations. The old beverage antenna, if you happen to have the real estate to put up a beverage, why not put another beverage next to it, located maybe a half wavelength distance, and run that into your noise canceller. Now you're going to be able to cancel the noise coming from that big lobe that the beverage antenna is pointed at.
So if we're talking about vintage noise cancellers, most of them had a tunable front end. This tube type noise canceller that I built, as you can see, it has a dual capacitor. The reason for having the variable capacitor is twofold. First of all, it's a preselector. The preselector allows you to just sample the noise signal that's on your frequency that you're trying to listen to, and it rejects a lot of other extraneous signals such as strong broadcast stations and strong ham signals that are close by to your frequency. The other thing it did is it's a way to do phase adjustment or phase control. As you tune a circuit, as you go through resonance, you can get a phase shift of upwards of 100 to 180 degrees. So this was a simple way to do phase adjustment as well. Unfortunately, this method does involve variation in the gain because you're sweeping through the tuned circuit's passband. So it's not a for free type phase control. Nowadays you'll see much simpler circuits used with these cancellers where they use a broadband front end. Now this worked to a fashion, but because of the problem of external interference signals off your frequency, well away from your frequency even, they've started to put in at least a high-pass cut filter on some of these boxes. So we're going to get into the intricacies of these circuits in the next video. We have to pick a circuit style to go into this box, and we have to make some decisions on how complicated. Someone said, I looked in the box and it looked like there was less than $20 worth of parts in there. Well, that's true, but you have to remember, what is that box doing for you? What's the sophistication of the box? Plus, this chassis alone cost $20, so we already blew the budget. Stay tuned for part 2, noise cancellation circuits.